How do you find the domain? We talked about this before the hurricane. The first one is a rational, the second one is a square root function, and the third one is what? What kind of function is the third one? Linear. How did we find the domain of a rational function? Say that again, I couldn't hear you back here. The denominator can't be 0 because there's one x value for which the function is not defined. How do we find that one x value? We set the denominator equal to 0, and I called this the restricted value. And if you solve for x, you get x equals -3. Now, how do we write the domain in interval notation? To positive infinity. So in words, this means all real numbers except -3. Write it in interval notation. So with a rational function, we have a restriction here. We have to pay attention to the fact that the denominator cannot be 0. How about this next one? What kind of function is that? Square root function. What's the square root of -64? 8i, but 8i is not a real number, and we can't really graph non-real number. It's a Narnia, so we have issues with square root function. How do we find the domain? Right, also called a radicand. So we set the radicand greater or equal to 0, and then we solve for x, and we have this inequality here. X is greater or equal to -5. If we start with -5 and go to the right, we get real y values. If we were to go to the left, we wouldn't. So how do we write the domain now in interval notation? -5, that is correct. Yes, and the last one is what? Linear. And linear function have a domain that are all real numbers. You are correct. So -infinity to infinity. Yes. Only if we had a -x or -3x, then you would flip the inequality. Like, for example, if you get the square root function that says 3 minus x, for example. 3 minus x, if you set 3 minus x greater or equal to 0, you subtract 3, and you get -x is greater or equal to -3.
You divide it.
And now you divide it by -1, and that makes it flip the sign, like so. So this graph, actually we're going to talk about graphs today. If 3 is here, this graph would be a reflection, like so. Because usually square root functions, they go to the right, but this is reflected. And it would be reflected across the y-axis, but that's beside the point, because it's not a parent function. So you have to take that in consideration. Oh yeah, good point. Well, you have my little yellow graph right here. How would you write the domain in interval notation? if you're now going to the x is less than or equal to 3, you're going to the left. Go ahead.
Negative infinity, comma, 3 bracket.
Yes, it would be. On a number line, let's say 3 is here. So it would be a bracket because 3 is included and it goes to the left. Yes. Cool. Good. Good. Anything else? I think that was the majority of 2.4. We will talk about increasing, decreasing in a little bit. So there are some bits and pieces that we have to talk about, and one of them is, I think it's over here, relative maximum and relative minimum points. And let me just give you a nice function. Just a plain, simple something to an odd power. You learned that in chapter 3, but here's a function. So when we talk about relative minimum and relative maximum, we're really talking about the highest and the lowest point within your graph, and that does not take in consideration this end behavior here going all the way down to the left. So it's just what is within your graph. If this graph doesn't stop, like this one doesn't stop, goes down, that's even lower than this point here, but we disregard that. The minimum and the maximum point are your points within the graph, not regarding the end behavior going up or down. So here, let's call this A, why not? And let's call this B. And this would be f of A, because that's, and this is f, let's call it of negative B, because we're down here. So this high point here would be a relative maximum. And the relative maximum, the value of the relative maximum is always the y value. The y value, but this book uses just the ordered pair. So the relative maximum here would be at A comma f of A, because that's your y value. And this low point is therefore the relative minimum. Sometimes you have more than just one minimum or maximum. That's why they're called maximum, minima. But here we have one. Relative minimum. And again, it would be the y value, so b comma f, and this is a negative, I call it just negative b, because it's below the x-axis. And again, your minimum is the y value. So if they are asking for relative minimum and maximum points, all you have to list is the ordered pair of these points. It's either your highest or your lowest point. And usually, where there's a maximum or a minimum, you also have what? A turning point. You can see turning points going up, and then the direction changes going down, or from down to up. These are the way I craft this yellow function here. This also includes turning points. Cool. So let's take a look at number 15. Or what about 15? Did we talk about 15 already?
No, I don't think we.
Okay, well, let's look at 15 then. I can ask you a bunch of questions. 15, first of all, is this a function?
Yes.
Although I haven't even written it down. Yes. This is a function. Okay, what is the domain? All real numbers, so we say from negative infinity to infinity. And why do you know that?
Because
Well, Jay was... Yeah, you answered the question.
Because the holes are filled in and there's no absolute values throughout every graph.
Everything is filled in, the holes are filled in, there is no discontinuation, yes, but there's also those little, these guys here that tells you they keep going and going and going. So, yes. What is the range?
5,
We would like to go with the lowest value first, so it would be negative infinity to 5. Is 5 parentheses or bracket?
bracket.
Bracket, because the holes are filled, right? Yes. Yeah.
I think it just depends on the book.
Yes. No, not with domain and range. That is always bracket or parentheses. That's in every book the same. Where it can be different is the increasing and the decreasing. Some books use brackets because the holes are filled. I like that. You have the solid points, or in some books just use the ordered pair or the parentheses like this book does. So speaking of increasing and decreasing, where is this function increasing?
Negative 3, 4.
Negative infinity.
When we talk about increasing, we need to say some kind of interval, Hannah. So increasing, I'm tracing it with my pencil and I'm going up until I hit a turning point. And down here, I'm going up as well until I hit this turning point. So it's increasing, and we look at the x values. So increasing on which interval? From negative infinity to
Negative 3.
negative 3, and there's another green from negative 1/2 to 2, positive 2, right. And then we got decreasing action going on. This graph is decreasing wherever my blue highlight is. Decreasing from,
4.
oh, you used the y value,
Negative 3.
negative 3 to
Negative 1/2.
negative 1/2, union 2 to infinity. That is correct. Yes, guys? Where do we have a maximum, a relative maximum, because it's within your graph borders and behaviors? You will, if you go to calculus, you will learn a lot about that. Yes?
2 from 5 negative 8.
Right, just list the points. So the points are negative 3, 4, doesn't matter which order you list them, and 2, 5. That's where your maximum occurs. Are these points turning points?
No.
Turning points. Are the maximum points turning points? Hannah, yes. Because they go from up and then they go down. And minimum, we have at what point? Negative 1/2, negative 2. Beautiful. Not too bad.
So would the turning points be the maximum and the minimum?
Yes, yes. This number 15 has 1, 2, 3 turning points. In chapter 3, you will learn what that means. If this graph has 3 turning points, that means this is a graph to the 4th power. The polynomial itself is 1 degree higher than the amount of turning points, but that is something for chapter 3, because in chapter 3 you're going to be able to graph these beautiful looking polynomials here. And you also have to get many more questions, like the amount of turning points for number 16. 1, 2, 3, 4, 5. There are 5 turning points. That tells me that this polynomial is to the 6th degree. Yes?
It's also like function.
Yes.
Under decreasing, why isn't that a negative infinity? And why is it a positive infinity?
Because you're thinking of the y value.
Because we were using the y value.
No, we have not used the y value anywhere, have we?
No, everything's using but
Yeah, we use the x value for everything for increasing or decreasing. Don't be confused by, yes, this arrow points down, you have negative y values, but your x values here are positive. That's why it goes to positive infinity. And over here, it still goes down, but your x values are negative infinity. That's why we don't say negative. If you were to say negative infinity here, you would look at the y values and not at the x values. But that is a good point. Don't get that confused. Everybody good? I don't want to talk about this one. Even and odd function. Now we kind of talked about symmetry already. Symmetric. We talked about graphs. And we talked about graphs that are symmetric with respect to the y-axis. That's all we're going to care about. And we talked about graphs that are symmetric with respect to the origin. Here is y and here is x. So this is y symmetry, this is origin symmetry. Now if we have a graph that is symmetric with respect to the y-axis, that's called an even function. Even functions are symmetric with respect to the y-axis. Odd functions are symmetric.
Wait, we talked about this in 2.2.
Yes, respect with respect with, I'll say it again, to the origin. Yes, in 2.2 we basically just looked at the graph and we knew if it was odd, even if it was symmetric with respect to the y-axis, or if it was symmetric with respect to the origin. Now we're going to look at this the algebraic way. How do we test if something is really odd or even? Now, yeah, we're going to look at that in a second. Remember, from 2.2, Hannah remembers it, we did draw a parabola. Now, a parabola is f of x equals x squared. So if x is 1, y is 1. If x is 2, y is 1, 2, 3, 4. Let's just get these 2 points. Now if x
was 0, y was
negative 1, y is still 1, and if x is negative 2, y is 2, and you're absolutely correct. If x is 0, then y is 0 as well. So this parabola more or less looks like so. And that's an even function because it is symmetric with respect to the y-axis because it's the mirror image. So what happens here is, right here at this point, to test see if something is even, we have the point 2, 4. And over here we have the point negative 2, 4. So what has to happen is we have to make the x opposite, negative, to see if the function is even. This one's even. What else did I say? A totally unscientific way of trying to figure out if something is even function or not is just looking at it, x to the 6 plus x to the 4 plus 3x squared. If all your exponents are even, it doesn't matter what the coefficients are, that's why I threw a 3 in there, but if all your exponents are even, then it's an even function. And it's symmetric with respect to the y-axis. Totally unscientific just by looking at it. The algebraic way is to test f of x is equal to f of negative x.
Question.
Yes.
What if the x had both even and odd? Like, would it be neither?
That is absolutely correct. If you have both exponents that are odd and even, then it would be neither. That is correct. So let's test this here. If I look at number 35, the algebraic way is the function that's given is f of x equals 2x to the 4 plus 4. Now, with what I just said unscientifically, you can tell me if this is odd or even already.
Even.
Yeah, without even testing it. But we're going to test it now. So we have f of x. Now we're going to change the x into a negative x and replace that in our function. And once we simplify it and those two are the same, then we can say for sure. So x becomes negative x to the 4th power plus 4. What is negative x to the 4th power? If it's positive x. It's positive x to the 4th power. Negative x times negative x times negative x times negative x. These two are positive, x squared, right? Times another negative x would be a negative x to the 3rd. Times another negative x is a positive x to the 4th. So negative x to the 4th is exactly the same as positive x to the 4th. And you can see that these two functions are now the same, which makes it even. So you're replacing your original x with a negative x and simplify that and hope for the best. Now let's take a look at odd. An odd function, the mother of all mothers of odd functions is,
The origin?
well, it's going through the origin, but the actual function is f of x equals what? X to the 3rd power. Hence, it's an odd exponent, therefore we know it's odd. But if I graph it, and let's say here's 8, -1, -2, -1, -8. What happens to my graph? It's symmetric with respect to the origin. We have points that are 2, 8, if I use that point, and we have points that are -2, -8. So not only the x value is changing, but also the y value. So to test if a function is odd, algebraically we say f of x has to be equal to -f of -x. That's the way we're testing to see if something is odd.
So if it was odd, the x would be just the x would be negative.
We're going to make everything negative. I'll show you in a second. Let me look at a problem in the book. How about this one? 37. In the book says f of x equals 5x to the third minus 3x. Now we're going to test if the left-hand side is equal to the right-hand side. Now negative f of -x, now we're going to put a negative outside the whole thing, and then 5 times negative x to the third minus 3 times -x. We're going to simplify that. Maybe I should write that. Hold on, let me write it on a different slide so it looks better. F of x is 5x to the third minus 3x. Without doing the fancy algebra, tell me what this is. Odd, even, or neither?
Odd.
Oh, there you go. So, on the final exam, the test multiple choice. Pick the right one. Yes, Jay? Because it's not, if I now, okay, this is not in the book, let's put a 1 here. It's still odd exponents, but this one's not odd anymore. Oh, let's test it. That's why we're testing it now. Because what happens here is the 1 shifts it up 1 unit, and it's not going through the origin anymore. Let's test it. So negative 5 minus 3 plus 1. I'm using a different color now. Negative x to the third, negative x plus 1. So let's simplify inside the parentheses first. I made my x's negative, and then we're going to distribute the negative. What is negative x to the third power?
Negative x.
Negative x to the third power. You are correct. So we have a negative 5x to the third power. I combined the two already. Times 5 is negative 5x to the third power. Then we have a negative 3 times a negative x. That is a plus 3x. And we have plus 1. That doesn't change. Okay. So we changed the x's to negative x's, and we simplified that. But now we also have to distribute a negative here. And this becomes positive 5x to the third minus 3x. If I didn't have the plus 1 there, I just proved it was odd. But because I have the plus 1 there, this now becomes a minus 1. And these two guys are not the same anymore. Not the same.
So it would be neither?
So this one is neither. With an even function, that doesn't happen. If you shift it up, it's still even. But with an odd function, yes.
So it either has to have all odd exponents and all even with no constant value, in order for it to meet a...
Rule of thumb, if you want to do it unscientifically, yeah.
Okay.
Let's be on the safe side. Yes.
How would it be odd if you didn't have the 1 there?
If, let's just, here you go. We don't have the 1 there. Now the green stuff, and let's just say we don't have the 1 here. The green stuff is exactly the same as the white stuff.
So if it's exactly the same, it's
No.
odd.
In this, yes,
Okay.
yeah. Let's put the 1 back up and the minus 1 right here. Yeah. So if you look at I wouldn't give you any of the other problems. So if I were to ask you on a test, is this odd, even, or neither? Then even, especially if it's a multiple choice problem, you can just pick, hopefully, the right answer.
That would be neither.
So now this one would be
Neither.
neither, because you can see in the nature of your exponents, you have odd and even there. That's neither. So Jay, to answer your questions, yes, you don't always have to. You can just look at it. Yeah. Okay, so that's odd, even, neither. What else is here? Oh, we already talked about that now. Okay. Difference quotient. Oh yeah, my favorite. There is a figure in the book on page 242. Took a picture of it. The difference quotient, Dairy Queen. We're omitting the average rate of change, but average rate of change, difference quotient is...
Sorry to interrupt, but is this 2.5 or 2.6?
No, we're still in 2.5.
Okay.
Yeah, there's a lot going on in 2.5.
Just needed
That-
to make sure for my notebook.
Right. They're all the same. And in immediate algebra, if you took that, you learned the word slope. Believe it or not, the difference quotient is the slope. But in intermediate algebra, if you think back, you only looked at the slope of a straight line. And the slope, therefore, of a straight line is the same everywhere you go. So now you graduated into college algebra, and soon, if you choose to do so, you will be in calculus. First 4 weeks in Calc 1 is all about the difference quotient. For college algebra, we're just going to do a couple problems to look at the mechanics of it. But the difference quotient is when you don't have a straight line. When you have curvy action going on. Look at all these polynomial graphs. How about a parabola? What do you know about the slope of a parabola? There is no slope per se like this thingy here, like this linear function here. So the powers to be back in the day, Mr. Gauss and Newton and all these mathematicians, they looked at curvy action, polynomials, and they came up, well, they have to have a slope too, right? Yes, so here we are, difference quotient. In pre-calculus, you start talking about taking the limit what really happens is, because the slope is really it's different in each spot. So what they do is they put a tangent line through it, and we're looking at 2 points, and basically what we're doing is we're just finding the slope or the difference quotient of this tangent line. So this is what happened, compare. And we make this is kind of an exaggeration. We make these values, these really, really small, and then we can find the slope in each spot, and that's the average rate of change. Why did she say no worries about the h? Well, how do we simplify this now? We can factor out an h, because that's what the top has in common. 2x plus h left all over h. And you can see that the h is now reduced to 1, and your dq for this is 2x plus h. And then in calculus, you learn about limits, and as h goes to 0, this h is going away, and therefore the average rate of change, the difference quotient, is just 2x. You will do this for about 4 weeks. Very tedious work, and then Jay is figuring out that we can do this all in 2 seconds. Then you're gonna learn a shortcut in calculus, how to do that. How do you like that? Nah. Okay, let's do 77. Come on, you can do it. 77, this one's for you. Last one. And then we go into 2.6, which is just looking at more functions. Graphing. 77. What is 77? I'm going to give you a minute or two. This one is a long one. 2x squared plus 3x. I can tell you the answer is 4x plus 3. How did I know that? Because I've done calculus for a long, long time. Okay, the only thing I'm going to help you with is f of x plus h. So now you're replacing your x's with x plus h squared plus 3 times x plus h. And that has to be simplified. Go to it. Come on. Which handwriting is that? I don't even know. Blake is here. Wow. That's not a great one there. All right, Blake. Okay, then. We can get on the there. I think I put grades there. I may not put a grade on there. Simplify. Mackenzie is not here today. Oops, so. Carlos, I gave you this back and you're gonna do your folder before the rain came. Nick, how are you doing? Oh, yeah. I think of the other one. Get your test back. No. Here was not good. So, what's the DQ? Okay. 2 times x squared plus 2xh plus h squared. That hasn't changed from the last time. 3x plus 3h. So now I'm going to distribute the 2, and that's 2x squared plus 4xh plus 2h squared plus 3x plus 3h. Woo! Don't you feel accomplished? And now we got to minus something. What are we minusing?
Minus 2x squared.
Minus 2x squared
And then
minus
minus 3x.
3x. There's something you want to practice. Now the book has a lot of rationals. Don't do rationals. Just make something up. Something that's a polynomial. Like 2 to the second power is about the highest difficulty we talk about. And also that you can expect on a test is more like something like this here, x squared minus 2. We can get rid of the cancel out and the 3x's cancel out. Let's write out what's left. 4xh plus 2h squared plus 3h all over h. And if you reduce an h, then you have 4x plus 2h plus 3 all over h, and your final difference quotient answer is 4x, didn't I tell you? Plus 2h plus 3, that has to be in no particular order, but here it is. That is your difference quotient. And how did I know that? I'm going to pause this right now. Okay, 2.6, library of functions. We got a couple minutes to talk about linear functions because we already talked about linear function. F of x equals mx plus b is a linear function. Well, it's a linear function. I already wrote it down. What makes it linear again? How, why, where, when?
It's a straight.
But I don't see that. Based on that, I don't know that is a straight line.
It's to the first power.
It's to the first power. Thank you. What happens if m is equal to 0? What do you have left?
Just the x.
Well, if m is equal to 0,
Oh wait, then you have no slope.
okay, you have m times 0. What is m times 0?
0.
So if m is 0, you
Oh, wait, you
only
do.
have f of x equals b left, right?
Mm-hmm.
Now that's also linear, but what kind of line is that?
It's a horizontal line.
Thank you. It's a horizontal line at whatever b is, so it looks like so. Here you go. Yep. Y equals b because
Yeah,
that,
like I said, it would be a straight line,
well,
which means it would have no slope in a way.
right, yeah, it's a flat line, yeah. That is correct. So here are your different types of linear equations. I didn't quite get the rest here. I guess I didn't take a picture all the way. They are out of the book. Here you go. So we have a positive slope if m is greater than 0. Positive. We have a negative slope. If m is less than 0, we have m equals 0, and that's f of x equals b. And the third one is what we call the identity function. If f of x equals x, meaning if y is equal to x. So these are our different types of linear functions. Up, down, left, right. Here you go. There you have them. Not a big deal. I don't know what that is, but that is a bunch of parabolas that are shifted up, down, left, right, stretched, and shrunk. Shrunk? What's the right
Small.
word? Shrinking?
Shrunken.
Yeah. Well, yeah. We and that's something we do in 2.7. So 2.6 is all about different functions we're going to talk about, library of functions. So let's draw a couple here. One of them is the square root function. We kind of talked about this one already a little bit, so let's talk a little bit more. Now, anything that's not linear, we got to make a t-table if we don't know how it looks like. So, and I made a t-table with those x values, and I picked those for a reason. Usually I go from -3 to +3, but in this case I do not, because then I would get Narnias, and I can't graph them. So I picked 1, 4, 9. Those are perfect squares. What is the square root of -1?
1i.
But we can't
But
graph
it would be
1i.
Yeah.
So that's a Narnia, not a real number in algebra. I can't graph that. What is the square root of 0?
0.
Square root of 1 is 1. Square root of 4 is 2. And the square root of 9 is 3. I picked those because those are nice and easy to graph. So we start at 0. Then we go 1, 1, then we go 4, 2, and 9, 3, and our graph more or less looks like so. It keeps increasing, it keeps going up. Can somebody tell me what is the domain?
0 to infinity.
Which is also the range, yes. This is what I call the parent function. We're going to look at the children on Thursday. These are the parents. Everybody good with this parent?
Doesn't it straighten out?
No.
This thing's gonna
No, it keeps going very minimal, but it keeps going up, up, up. Yeah. No, it's if it were to straighten out, then it would be linear. That can't be the case. Next one is the cube function. I don't want to really get into the cube function.
Because it's an odd.
Yeah, that too. But we already talked about the cube function, so the cube function looks like so. And the cube root function more or less looks like so. I'm not a big fan of cubes or cube root functions. Yeah, exactly. Cube function, cube root functions. And again, if you want to be exact, make a t-table. What do we know about domain and range of cubes and cube root functions? They're the same. Come on. What do we know about this? The phone isn't going to tell you that. Maybe it is, but what is the domain? What is the range? Negative infinity to infinity for both of them. Yes. Okay. Next one.
Is it the same for the cube root?
Yes, it's for both of them.
Okay.
Yep. How about this funky looking absolute value function? And these are all parent functions. There's no shifting going on just yet. So if the absolute value of -3, what is that? 3, 2, 1, 0, 1, 2, 3. Right?
A U.
No, it's not a U. The reason why it's not a U, an absolute value function looks like a V, because really what happens is you make two linear functions out of it. One is a positive x and one is a negative x. But the domain and range are exactly the same as the U function. So what's the domain here?
Positive infinity, negative infinity, or negative infinity and positive infinity.
Yeah. What is the range?
Same.
No, not the same. You don't have negative. It goes from 0, because it starts at 0, to infinity. Again, this would be the parent function. And do we have time for one more? We get them all in? We've done the parabola already. So if you want to be you can make a t-table. -3 is 9, -2 is 4, -1 is 1, 0, 1, 2, 3, 0, 1, 4, and 9. Beautiful it is. 2, 1, 2, 3, 4, and we talked about this one. I gotta bring in my template. I bought a template of parabola once. I've seen it in the store. Now, the domain and range is the same as it is for the absolute value, -infinity to infinity, and the range is 0 to infinity. And this is my parent, this is a parent, this red one is the mother of all mothers of functions. And here they are from the book. Check them out. You see domain, range. This is a square function, the parabola, decreasing, increasing. It's an even function. Cube, absolute value, square root function. Those are our main functions we're going to work with. I'm not talking about rational functions in 2.6 because they have their own section coming up in chapter 3. On Tuesday, we're going to talk about what piecewise functions, and we're done with 2.6. Any questions?